All right, guys, let's continue with part 2. We now look at the zero order reaction, right? Okay, consider this reaction. A changes to B, all right? And the rate of reaction is rate constant and concentration of A to the power of 0. Okay, anything to the power of 0 is 1, so our rate is actually equals to rate constant. So what this means is that the rate is independent of the concentration of A, and A is simply being used up over time. As you can see from the right, when we plot concentration of A against time, it just goes down gradually. Okay, but the rate is a straight horizontal line when we plot it against concentration of A. So this means that no matter how much we increase the concentration of A, the rate of reaction stays the same. Okay, it is regardless of, it ignores basically the concentration of A. Okay, so that's your zero order. Okay, this is not that important, but we just got to know about it. Okay, next we look at the important first order reaction. All right, so this rate of reaction, right, is directly proportional to the concentration of the reaction. All right, so what this means is that if we increase the concentration of that reactant, it will increase the rate by the same extent. All right, so you can see when we plot the rate versus concentration graph, right, is actually a straight line up. So let's say we have concentration 1, the rate is equals to 1, concentration 2, the rate will go up to 2. All right, and so on and so forth. Okay, then also keep in mind that if you plot the concentration of the reactant versus time, it will show a steep decrease because the rate is very fast, right? It's the fastest in when t equal to 0, and then it plateaus off to like almost a horizontal line after some period of time. Okay, and the product concentration versus time graph shows pretty much the same thing. As A decreases, B increases rapidly, and after some time, it also will start to plateau off. All right, units for the rate constant is per time. Okay, time being seconds, minute, or hour. Okay, what is the characteristics of a first order reaction? It is what we call a constant half-life. But basically, what's a half-life? Right, the half-life is defined as the time taken for the concentration of a reactant to decrease to half its original value. Right, so for first order reaction, right, we have this particular formula: T half equals to ln 2 over K. Okay, take note that this is only applicable for first order or pseudo first order reaction. All right, pseudo first order, I will teach you later what is that. First, let's look at the graphical determination of T half for first order reaction. So you can see that concentration of A, right, decreases to half, and it takes a certain amount of time. And then it decreases by half again to 1/4, and it takes the same amount of time. Likewise, when you decrease to 1/8 of the initial concentration, it takes exactly the same amount of time. All right, so this is what we mean by having a constant half-life. The time taken to half the concentration is the same throughout. All right, so you see that for product versus time graph, but with a little bit of difference. All right, so instead of starting with initial concentration, B starts with 0, right, because it's the product, and then the time taken for it to get to half of what? Half of the final concentration, all right, the final amount that will be produced. Okay, so you can work out this final amount through actually your balance equation. Okay, so half, and then it takes a certain amount of time, and then for it to get to 3/4, again a certain amount of time, for it to get to 7/8, a certain amount of time. Okay, so to calculate the number of half-life taken that we need, right, to reach a particular concentration, because sometimes question will ask you, how long would it take, right, to reach a certain concentration? You can basically use this formula where n, right, is equals to number of half-life, and C subscript T is concentration at time T, C naught is the original concentration. All right, so let's try out a quick check. Okay, they say that the decomposition, right, of hydrogen peroxide is a first order reaction, and it has a half-life of 8 hours. All right, how long does it take for the concentration of peroxide to decrease from 4 to 0.1? Okay, so we're going to use this particular formula. We're just going to plug in the figures, and then you will notice that the number of half-life is not a whole number. It does not have to be. It's 5.32. And because the question already told us the half-life is 8 hours, so 5.32 half-life will basically yield us 42.6 hours. All right, so that's it for first order reaction.